Howdy students, welcome to chapter 6. In this chapter, we will put together what we learned in chapters 4 and 5 and cover a few important concepts that you need to fully understand the climate change problem. Up to now, all of our calculations have been what we call equilibrium calculations. In other words, we explicitly assume that energy in equals energy out and derive everything from there. But we don't live in an equilibrium world. To understand what's going on, let's consider the following scenario. Let's imagine a planet with no atmosphere that is in equilibrium, meaning energy in equals energy out. Let's further assume values for the Earth so that we know that energy in and energy out are both 238 watts per square meter. We calculated in chapter 4 that the planet's surface temperature would be 255 Kelvin. The energy fluxes for this planet are shown on this slide. Now let us imagine that a one-layer atmosphere is instantly added to the planet. What are the fluxes the instant after the layer is added? Energy in for the planet doesn't change. It's still 238 watts per square meter. An instant after the atmosphere is added, the temperature of the surface is still 255 Kelvin because objects have thermal inertia, which prevents their temperatures from changing instantly. This is the same reason it takes several minutes for water in a pot that you put on the stove to start boiling. This means that the instant after the atmosphere is added, the surface is emitting exactly the same as it was before, 238 watts per square meter. The atmosphere, however, is now absorbing all of the photons coming from the surface. Half of the observed energy is re-emitted upward to space, and half is re-emitted downward back to the surface. This means that the atmosphere is emitting 119 watts per square meter out to space and 119 watts per square meter back to the surface. If we look at energy balance for the entire planet, we find the planet is no longer in energy balance. The planet's energy in is 238 watts per square meter, but energy out, which comes entirely from the atmosphere, is 119 watts per square meter. This means the planet is accumulating energy at a rate of 119 watts per square meter. We can also look at energy balance for the surface. Energy in for the surface is 238 watts per square meter from the sun and 119 from the atmosphere, while energy out is 238 watts per square meter. Putting them together, we see the surface is also accumulating 119 watts per square meter. Because energy in is greater than energy out, the temperature of the surface must also be increasing. So after a while, enough energy is accumulated to warm the surface to, just as an example, 270 Kelvin. At this point, the surface is now emitting 300 watts per square meter upwards, and the atmosphere absorbs this and radiates half upwards and half back to the surface. For this planet, energy in of 238 watts per square meter still exceeds energy out of 150 watts per square meter. But the difference is now 88 watts per square meter. It's smaller than it was when the planet's temperature was 255 Kelvin. However, since E in is still larger than E out, this means the planet is still warming. So now let's imagine that a little while later, the planet is now 295 Kelvin. Please pause the video and work out the fluxes on the arrows. Something like this will be on the exam, so it's important you know how to do this. So here are the fluxes. The surface is 295 Kelvin. So from sigma t to the fourth, we can calculate that it must be radiating 429 watts per square meter. The atmosphere absorbs this and radiates half up and half down. So those fluxes are half of 429 or 214 watts per square meter. Energy in is still 238 watts per square meter. So the energy imbalance on this planet is now 24 watts per square meter. Because E in is still larger than E out, the planet is still accumulating energy and it's still warming. But note that as the planet warms, the energy imbalance is declining. So I think you can probably see where this is going. Let's imagine the planet reaches 303 Kelvin. At this temperature, the surface is radiating 476 watts per square meter. The atmosphere absorbs this and radiates half upwards and half downwards. Energy in for the planet is 238 watts per square meter, and energy out for the planet is 238 watts per square meter. Energy in now equals energy out, and the planet now stops warming. We have reached a new equilibrium temperature. So this is the key thing to understand. If energy in does not equal energy out, then the planet's temperature will adjust in such a way as to wipe out the energy imbalance. This summary slide shows how the addition of an atmospheric layer to a 255 Kelvin planet, which generates an energy imbalance, warms the planet until it reaches 303 Kelvin, at which point the planet is back in energy balance. A different way to look at this is to ask the question, why is the climate of the Earth what it is? The answer is that the climate we have now is the one that sets energy in for the planet equal to energy out. But as we saw in chapter 5, and we'll discuss further in this chapter, humans are perturbing the energy balance of the planet by adding greenhouse gases, which is increasing the number of layers in our atmosphere. As a result, the planet's temperature is shifting, which you saw in chapter 2. This is climate change. One thing you might be wondering is how long this process takes. To answer this, let's look at an actual climate model, a detailed computer simulation of the climate system. We'll talk more about these in chapter 8. The planet being simulated is initially in equilibrium. The left plot shows that the temperature is not changing, and the right plot shows energy in minus energy out, which is 0, indicating that they are equal and the planet's temperature is therefore not going to change. Now, let's imagine that we suddenly add a lot of carbon dioxide to the atmosphere in year 2000. This is similar to the example above, where we added a layer to the atmosphere. Now we see that energy in suddenly exceeds energy out, in this case, by 7 watts per square meter. But the temperature doesn't respond instantly because it takes time for the climate system to warm up. So we know that the planet is going to warm up. We see that the ocean's mixed layer, the relatively shallow layer on top of the ocean, which we talked about in the last chapter, warms up rapidly. So in response to this addition of carbon dioxide, you get an initial burst of warming. Once the mixed layer has warmed up, additional warming requires warming of the deep ocean. This is a much slower process because the deep ocean is very big and it takes thousands of years for the climate system to fully warm the deep ocean and reach a new equilibrium. In the next video, we'll begin quantifying how humans are perturbing the planet's energy balance. And now, your moment of dog.